Today we'll discuss about blast analysis of a column, and the problem statement is we have a column of 3-meter height, which is having a cross section of 300 mm height and 300 mm width, not height, length and width, uh, and then 3 meter of height. So to that column, we are applying a blast charge of 6 kg and at a standoff distance of 1.81 meter. And it is kept at the mid height of the column. And the support condition, we are considering fixed condition at top and bottom. And the material parameters, material properties will take the same as yesterday's problem. And this one I just kept so that you will have an idea again what are the steps involved in LS-DYNA analysis. First is pre-processing. We'll define the geometry, material parameters, boundary condition, loading, and all the solution and output parameters. Second step is to do the LS-DYNA analysis, and finally post-processing. And just keep in mind that you will be using this consistent set of units. So the first step is define the mesh. So you can go to this right side toolbar in which you can see the meshing option. You click on the mesh, then and the next section it will show the sub tools. So in which you can select the shape measure. And when you open the shape measure, you can see this box. And in this box, you can see a entity as a box solid. So today's column will be modeling model using solid elements. So since it is solid elements, we'll just use the box solid entity. And here you can see the region, and in you select the region, and in here you input the value coordinates of your column. And since our column is 300 mm size, I'll just provide the origin of the coordinate 0, 0 at the center of the column. It's always better to provide your origin at the center of the column so that makes your calculations easy. So here I provided minimum x coordinate as minus 0.15 and the maximum one is 0.15. Again for the y coordinate, since I provided at the origin, origin at the center of the column, y is also the same value. And z direction I provided 0 at the bottom of the column and the total height is 3. So z value will range from 0 to 3. You can also provide at the mid height of the column. In that case, it will be minus 1.5 to 1.5. So once you input all the coordinates of the column, you can go here. And here I selected element size as the option. You can also select the number of elements, in which case you will be inputting the total number of elements along the x direction, y direction, and z direction. But here I provided size of the element. So I provided a very coarse mesh, which is around 50, which is 50 mm of size. So along the x direction, y direction, and z direction, I provided a value of 0.05. And then you provide the target name, which is column, and target part ID. And after that, you can click on create. So once you click the create, you will have a trial mesh. You get a trial mesh. There you can check whether your geometry of the column is right. If it is okay, directly go to this box and click the accept button and then click the done. So now you will get the column geometry as it is, in which the meshing, the elements of the column is also visible. And the next step is to define the material properties of the model. So again, you go to the model and part section, and here you go to the subtool section and select the keyword. So from here onwards, all the parameters, all the properties of the column will be providing using the keyword manager. So you open the keyword manager As I said yesterday, you will like directly you will see the selection as model. So which shows the keywords that is used for your model. Since we have just created the model geometry, will have elements, node, and part. As part is only one part. So you select you change the selection from model to all. Then you will see the list of keywords available in the keyword manager. From there, you can select the material option. Again, you click on the positive button. You see the list of material models available in LS-DYNA. And from here, you can select the plastic kinematic, material plastic kinematic, which we have used in yesterday's problem also. So the same material model we'll use today, and the same material properties we'll be inputting here. So when you open plastic kinematic material model, you can see the title, you can see this box and provide the title as steel, material ID 1. And the properties I have provided in the problem statement slide. So density is 7850, modulus of elasticity is 2.07 to 10 to the power 11, Poisson's ratio 0.3, sigma y is 300 MPa, and tangent modulus is 1a plus 9. And once you provide all the details, you click on accept button and click done. If you have more number of material models, just click add to add more number of models. And next step is to define the section properties. So go to the in the keyword manager, go to section area. So click on the section keyword, and then the list of sections are available. So here we open the solid section because we are using, we created solid elements. Yesterday we selected shell elements because our elements was we model using shell elements. So here you go to the element formulation using solids. And when you open the solid section, you can see this dialog box. So here you provide the title, which is column, and then section ID also you provide. And here you can see the element formulation. So element formulation, as I said yesterday, it is actually basically the integration rule, which kind of numerical integration you are using. So we'll keep the basic single integrated element. So here I have shown you like what is element formulation one. Basically, it has only a single point for we'll integrate using Gaussian rule for a single point. And if you want to know what is meant by different element formulation, just click on this element formulation. Then at the bottom, they'll show the list with a brief description. So you can see here equation 1 is constant stress solid element, and in bracket they have provided default, which is the default element formulation used for solid elements. And AET, you don't have to fill, that is for fluid dynamics problems. So you can just leave it as 0, accept, and then click done. So yeah, in yesterday's problem, okay, one more thing. In yesterday, we have to provide the thickness of the shell because we just created like a plain element. We did not provide any thickness for the element. But since for our brick element, solid element, we already have the like all the dimensions. So we don't have to input any of the cross-sectional parameters here. And the next one is something that I didn't discuss yesterday, which is about hourglass control. So I'll just give you a brief idea of what is meant by this hourglass control and why we use it. Since we use this single integrated element, so if you consider this as your element, we'll just take the stress strain values at the center of this element. Since you have only a single point, we'll take the stress and strain at the center. So sometimes the elements will deform in such a way, like the way you have seen, like I've shown here, the element will deform in such a way that at the center where your integration point lies, at that point there will not be any deformation. You can see here this section is moving and this side is moving, deforming, not moving, and here also it is deforming. But at the center you can see the length is same. So since there is no deformation, it will show zero strain for the total element. And since it is zero strain, it shows zero stresses. But actually, the column, the elements are deforming. And when the elements deform in such a way, the response will be something like this. It's like an hourglass shape, but in actual case, the column will deform like this is not an accurate deformation pattern. So this is something that is related to numerical issue. It's not a real deformation or anything. So it's a numerical issue. So we resolve this issue by just providing some forces at the corners where you will be having this unrealistic deformation. We provide some internal forces. So here it is, I have written, can be controlled by invoking suitable hourglass control algorithm that creates internal forces to resist hourglass mode. So this control algorithm, it creates some internal forces and it reduces this kind of a deformation. So two kinds of algorithms we use generally, viscous forms and stiffness form. But since our loading is blast loading, which is a high strain rate problem, we provide usually viscous based control algorithms for hourglass control. So this is just a theory of or a basis of hourglass control. And if you next step, so I discussed this one because we have to provide hourglass control for the solid element problems. So the next step will be providing hourglass properties of the model. And here you can see, you go to the keyword manager. Here you can see the hourglass option. You click on the hourglass option. You can see only one option is there, one keyword is there. So you click on the hourglass mode. And next, you can see this box. So here you define the hourglass properties of the model. So which is basically, you just have to provide the title and then hourglass ID. After that, this is the area where you will be providing the algorithm for controlling hourglass. So if you click on IHQ, again at the bottom you can see the list of algorithms provided for hourglass control. So we'll use the default value, which is 1, and you can see here, which is a standard LS-DYNA viscous form. So just select the IHQ value as 1. Remaining all parameter, you can keep it in the default mode. Just click accept and then click done. And now we have all the, we have applied, provided the section properties, material properties, and hourglass control algorithm. So we have defined all the parameters and everything. Now we just have to assign these parameters and properties to the column part. So you go to the part column and click on this part section, part keyword, and you go to part. And if you open the part keyword, you can see this box in which you provide, like I discussed yesterday, you just give the title as column, provide part ID as 1, and then click on this black dots, which will, if you click on this black dots, it will automatically open the list of section properties that you have provided. We have provided only one, so select that one, and here you can see the material ID. Do the same thing for material ID. And for yesterday's problem, we just selected these two values, material ID and section ID. But here we need to provide the Hourglass ID also. So from here you select the Hourglass ID, click on accept and then done. So the next step is to apply the boundary condition. So a boundary condition, it needs some some other sub steps, which is, as I discussed yesterday, creating the entity set. So we need to tell LS-DYNA to which nodes we want to apply the boundary condition. So for that we create a set of nodes. For that you can go to, if you click on this model tool, from here we have already selected keyword manager. At the bottom of this you can see the create entity option. You click on the create entity, then this box will come and click on the set data. So here the list of set data are there, which is set node, beam, solid and everything. So if from here you click on the set node option, and once you click the set node option, you can see here show, create, modify, modification and deletion option. Click on the create button, and then your window look like this. So you can go here, this box, and select the area option. Area option is basically you select the nodes using area. So you can do one thing. You can, this is actually the column is it shows the front view of the column. So I kept in such a way that I can select the top nodes using this area method. So next step is to select your top nodes where we'll be applying our boundary condition. And when once you select this nodes, you go here and click apply. And after apply, you click on done button. So now you have created the node set for your top boundary. Same way, you can create the bottom support nodes. So again, now you have already created the top boundary. You can see here the top boundary, which consists of 49 nodes at the top. Again, you go here, you have to create the second one. You provide the section ID, you provide the name, which is optional, bottom boundary. But if you provide, it would be very easy for you to assign the boundary conditions later. So you provide the bottom boundary name, and again come here, you select the area method, and this is the bottom support of your column. Select the nodes at the bottom support using area selection method, and again you go here and click apply. So here when you click apply, you can see that your second set of nodes, which is the bottom boundary nodes, will be get selected, and you click on done button. So now we have selected the node set which we require for the boundary condition. And now we have to apply or assign the restraining to all these nodes. So you go to the keyword manager. From the list, you take select the boundary manager, boundary keyword. And when you open the boundary keyword, you can see here SPC set. SPC set, when you click on that, you can see this box in which it shows like the boundary condition, how the option to provide boundary condition. And here you provide ID as one, and the title is top support. And here you can see, if you click on this black button, it will directly go to the set of nodes that you have already created. So in our case, we have two sets, top boundary and bottom boundary. For the top support, you select the first node set, and from node set, and then you apply the restrain condition. So ours is fully fixed condition. We restrain all the translational and rotational degrees of freedom. So all the X, Y, Z translation and rotations will keep it as restraint. So there are 0 and like 2 options for restraining. 0 means we are keeping that degree of freedom, like it is free, and 1 means we are restraining that particular degree of freedom. And okay, so now you have this top support boundary created, and you have to create the bottom support. So again, you go to this button, add button. So when you click on add, a new set will come. Here you can provide the second ID, bottom support, a name as bottom support. Again, here node set ID, now we will select it as the second one because it's a bottom support. And again, the same way, the support, bottom support is also fixed. So we'll restrain all the degrees of freedom. So we provide 1 for all degrees of freedom. And here you can see now we have created top support and bottom support. And the next option is actually applying your load. And as I told you in the problem statement that we'll be applying a blast load of charge mass 6 kg and kept at a standoff distance of 1.8 meter. So there are two ways in which we can apply blast loading to the column in LS-DYNA. One is considering the blast load as an idealized triangular pulse load, and then second one is directly applying it as a blast load. So I'll discuss the two methods here. And first one, for the first case, we'll consider it as an idealized triangular pulse. And for the same, like we'll compare if we consider it as a triangular pulse load, how the response of the how the column will respond, and if we apply the blast load directly, how the column is going to respond. So to define the triangular pulse load, we need to define the load history. So if you go here, you can see in the keyword the define option. So you click on the define keyword, and then the list will come, and here you click on the curve option. So if you click on this curve, you get this box where we need to provide the load history. So the title of the load is triangular pulse. We'll keep it as triangular pulse, and you provide the load curve ID as 1. And here the along the abscissa and ordinate, the scale factor will provide as 1, a value of 1. And here, as I said yesterday, you put the XY values in the abscissa and ordinate section. Here, our triangular pulse load is 0. Initially, at 0 time, the value will be 0, and then there will be a sudden peak, and then it will drop down to 0. So first we will input 0, 0 value. Then you click on insert. And again, this is actually when we draw a triangular pulse load, this will be like at 0 itself, it reaches its peak value. But if you provide the peak value at 0 again, it will lead to some numerical instabilities. So because of that, we'll just provide we provide, this is actually 1 e minus 5 value. So at 1 e minus 5 time, we provide the 1, which is like it reaches the peak value. And we consider the triangular pulse as a 1 millisecond duration pulse. And so the final value will be 0.001, which is 1 millisecond. At 1 millisecond, it will reach to 0 value. And you insert all these value, and then you click on accept button and then done button. So when you apply the blast loading, if you consider your column, the blast loading will be applied throughout the face of your column. So for that, we need to select the node set. We'll apply the blast load using nodal values. So for that, we need to create again entity set. So the set of nodes to which we will be applying this triangular pulse load. So we go to create entity section, the keyword, we click on the create entity. Like we did for the boundary condition case, we go to the set data, and then we'll click on this set node option. You go here, click create button, and then you get a window like this. So here, this is my column, and for the column, we'll be applying load throughout the face of the column. So to select the nodes throughout the face of the column, I'll just take the uh, top view of the column, so that if I select this particular node, the entire nodes will be selected. And here you need to you have to keep in mind in what phase you have selected your node, node set. So if you say here, this is your X and Y direction. So if you consider, we have kept our origin 0, 0 at the center of the column. So if you see here, this is the direction, like positive Y direction, we are applying the blast load. But on the other hand, if we are selecting this face of the column, this will be negative Y direction. So you have to keep in mind which direction, like the phase that you are selecting for the application of blast load, which direction it is, we are applying the blast load. So you select this set and go here and click apply. And next one is, now we have the set of nodes for which we have to apply the blast loading. And we also have the load history for the loading. We have already defined the curve definition, load history for the triangular pulse. And then we selected the set of nodes for which we'll be applying the blast condition. And now we actually have to apply the load value, the nodal load, to the set of nodes that we have selected. So you go to the load keyword, click on this positive plus button, and here you can see node set. So we'll apply our blast load as a set of nodal loads. And if you open this node set, you can see this box here, the node set ID. It will show. It will ask for the node set ID to which we'll be applying this nodal loads. So we have created a blast load node set in the previous slides. So we select the node set ID as 3 and your degrees of freedom. If you click on this degrees of freedom, it will show you like 1 will be X direction, 2 is Y direction, and 3 is Z direction. So ours is in Y direction. We'll provide 2. And load curve ID, that we have already defined the load curve ID. We'll select the ID, load curve ID as 1. And here the scale factor section. Here is actually where we provide the exact value of the load. So in load history, we just provided it as a 1. It has a peak value of 1. So now we'll provide a scale factor, which is like 1.054 into 10 to the power 4. So which will be around. Okay, one more thing. So how you calculate this scale factor is also important. So for the load condition, for the blast loading that we have considered, it is actually a 6 kg column, a 6 kg charge mass kept at a height of, kept at a standoff distance of 1.81 meter, which will, the reflected pressure will comes around 4.27 if you calculate using the KB chart. So for to like approximately equate the nodal blast load using the triangular pulse and the direct blast load, I just provided a uh, total nodal loads of 45,000. Not 45,000, 4,500 kilonewton. So this your column will be subjected to a total load of 4,500 kilonewton. So that 4,500 kilonewton will be applied as a nodal loads throughout the face of your column. So you apply it as a nodal loads to 427 nodes. At the face of your column, you can see like when you select the number of nodes, you can see a total of 427 will come. So we divide the total 4,500 kilonewton to 4,500 kilonewton by 427 nodes. So which will come around 1.054 into 10 to the power 4 Newton. So this scale factor you provided here, then you click accept and then you click done. And then you have to define solution control parameters. So which determines the solution, like your solution. So here you go to control, you click on control, then you can see termination and time step. These two parameters, keywords we have to select, and in termination, we provide the end time, the total time duration of your analysis. And since our loading is only 1 millisecond, we'll keep a total duration of 50 millisecond. 50 millisecond will be sufficient for to get the response of the column. So we keep it as 0.05, which is like 50 millisecond. And then you click accept and click done. And next one is providing scale factor for the time step. So this value you keep, this is the default value. So you keep it as the default value itself, and then you click accept and then you click done. So now that we have provided all the parameters that are required, all the keywords that are required for determining the solution of our problem, the only parameter that is the left is the output parameters. And these output parameters I'll be discussing in detail today because we are focusing more on the post-processing session today. So here you can see a number of output parameters are, we need to define a number of output parameters. And as I said, output parameters are the parameters which actually define the output, how you want your output response parameter, like the response of the column, how you want, in what interval you want your response history. All these things will be defined in the output parameter section. So if you go here, you can see database option. So in database, if you open, the first option is ASCII option. So here, if you open the ASCII option, you can see this window. This is actually how we're telling the software what outputs we actually want. EL out is element output. So we want element outputs, which are the stresses, strain values. So we'll provide a tick in here in the EL out option, and then we provide the DT value. DT value is just at what, how many response values you need, like at what intervals you want to get your response values. So we provide it as 0.1 millisecond. So here you can see 0.0001, and you keep it as a binary, you keep it as 1, and you accept this one. And likewise, we have to select the next output parameter, which is node out. Node out is your nodal output values. So basically, all the velocity, nodal displacement, nodal velocity, you'll be getting all these value if you select this node output. And then again, you provide the DT, output interval, at what interval you need these values. So you provide the same DT value for all these output parameters. You can click the binary, and then you can go to section force, SCC force, which means the section forces. Section forces are if you consider a section of the column, like midsection, top section, what would be the moment that the column will be having during the blast loading, the shear forces, all these force values you will be getting from this section force parameter, and you keep the same dt value and keep the binary as 1. And finally, after providing all this value, you just have to click on accept and then done button. There are other response, like output parameters are also here, like you get different you have different options to generate different response values, but we'll just focus on the three values, which are nodal output values, nodal displacement, then element displacement, and finally the section forces. Now the other output parameter is this we have discussed yesterday in database. You go to binary D3 plot, and if you open the binary D3 plot, you can see the D3 DT value. For binary D3 plot is the output at which like when we play the response of the column, you can see different damage status. So this D3 plot, it determines the DT value in D3 plot determines how many damage state we need to see. So you provide a DT value, a higher DT value for D3 plot, and then okay. Now we have provided the node output, like we in ASCII option we have provided three output parameters. One is nodal one, and the second one is element output, and third one is sectional forces. So now the software know you need these three response parameters, but it doesn't know at what locations you need these parameters. So LS-DYNA, it won't calculate the values for throughout the column, or like for all the elements or all the nodes, it won't calculate. The ASCII value, it calculate for the location that we will be telling the software, like this location, I want the history, nodal displacement, and this section you want the element element like stresses and strain. So here we'll discuss about how to define the locations for getting this response value. So this is same as creating an entity set for the load or boundary condition. So same way, we'll create the entity set, basically set of nodes and set of elements. And then we'll tell the software, okay, we have the set of nodes and elements. You need to find the response parameters at these locations. So here you go to create entity in the same way that we have done for boundary and load set, load node set. You go to create entity, open the set data, you select set node. And when you select the set node, you select this create option. Again, you will get a window like this. And here you select the area option. And now we inform the software that we want the nodal response parameters for this set of nodes, which are at the mid height of the column. We'll provide we select the nodes at the mid height of the column, and then we click apply. So here you can see we already have blast load all this set of node set, and we'll just provide another set of node set. And then when you have finished selecting the node set, you go to database, and then you go to history node set option. So here you tell the software that at node ID 4, you want the nodal history. So here you click on this button, then it will show the list of node set from which node set we want the response history. We select that one, and then we'll click the insert button, accept, and then done. So now we have the node set response. Like we already informed the software that we want the nodal response history, and we also inform the software at what location we need the response history. Next one is we in database we have mentioned we want the element output. So now we have to inform the software at what location we want the element output. So again, you go to create entity, you open the set data, and here in the list of set like entity values, we already use the set node option. But now we have to create a set of elements. So ours is solid element. So we'll go here and we'll select this set solid. So here I have shown set solid option is selected, and then similar to the nodes set node option, you go here, click on the create button, and you get a window in say similar to the node set option. You click on the area, and then we select the midsection no, elements, and then you click on the apply button. So here when you click the apply, you will get the set of elements here. Again, we have to inform the software the location at which we'll need the element output. So you go to database, history solid set, and you select the ID number for the set of elements. Again, click on insert, accept, and then done. And the final one is the cross-section set. So in database, we have provided nodes, node set, element set, and there was section force also. So node and element, we have already provided the information of location, but for section forces, we haven't provided. So you go to database, you click on this cross-section set. And for the cross-section set, you get this window. But for the cross-section set, we need to define or we need to show the location of node set as well as the solid set for which location or for which section we need to find the force. So you go to here, 1 minute. So in the previous section, I have shown like how I have selected the node set and solid set. So you can see here the set of nodes and solids. These both are for the same section. I have selected for the same section. Here you can see the solids and the nodes are for the same section. And when you define the cross section property, you need to have the set of nodes and the set of solids at the same section. So if I want to if I want to find the sectional force at the midsection, I should select the node set and the solid set from the same section. And then once you select this node and solid set, you accept this, you click the accept button and then click done. So this is how you do your pre-processing for the column subjected to blast load. And the final stage is to save your .k file. So you go to file option, save and save keyword. And next step is to do your LS-DYNA analysis. So you go to LS-DYNA manager. You can see the solver option. You start the LS-DYNA analysis, and here you provide the run, and you have to select the file. And remaining all you can provide the default values. And when your analysis will be finished, it will show normal termination. And for this column analysis, if you take the same element size and all the properties and time duration, like load time and everything, it will take less than a minute to solve this problem. So the next step is now you have solved the problem, and now we have to post process our result. So for that, as I explained yesterday, we have to reopen LS prepost from the file menu, select open and then LS-DYNA binary plot. And from the list, you select the D3 plot file and open it. So when you open the D3 plot file, you'll find a window like this. So here you can see the display button in which if you click on this forward button, it will show the response of the column, the graphical response it will show. And the same way you can now do the fringe plot analysis. So for that, you go to the post processing option and then you go to the fringe component. This we have discussed in yesterday's tutorial also. So we select, there are a number of parameters for which this fringe value will be shown. So we select the von Mises stress. See, if you see the select the von Mises stress, you can see at the center of the column, we are getting a maximum damage or the maximum stresses. And the next option. So in the output parameters, we have informed the software that we need three output parameters, which are nodal values, element values, and section values. Now we post process these values so that we get the response from the response of the column. So for that, we go to this post option and then here, if you remember in the database ASCII option we selected. So we click the post button and then we select the ASCII option. So ASCII option, when you open the ASCII option, you can see all the list of parameters that we get. But you can also see this asterisk in near to node out, element out, and section force, because these three parameters we have already defined in the pre-processing section that we want the response for these three parameters. So if you click on this node out button, node out, if you select this node out and then you click the load button, it will load the number of nodes that we have selected to get the response. So we have selected for this problem, I have selected at the top and mid section of the column, and it will show all the node values, node IDs. And if I want to get a displacement response, I select the node ID. I selected this node ID of 1515, and then I want the displacement in the y direction. Y displacement I want. So I click on the Y displacement and then I click the plot option. So when I click the plot option, I'll get the Y displacement that is obtained for this particular node. So this is the nodal displacement history that I'm getting for the 1515 node ID. So here you can see the displacements are it's almost in an elastic state. So you can see the displacements are in terms of millimeters. So a maximum millimeters of around 1 to 1. Maximum of 1.1 will be there. So it reaches a value not 1, 1.5. So this is how you get the displacement history. And next one, like that, you can obtain the displacement history for different node IDs, like mid height you can obtain, a node at the top end of the column you can obtain, and node at the bottom end you can obtain. And next one is obtaining the element output parameters. So we have already obtained the node out. Next one, we'll obtain the element out. Same step. You go to ASCII post, you go to ASCII, and then you click on this, select the EL out button, EL out, and then you click the load button. Then it will load the list of elements that we have already defined in the pre-processing stage. And from here, I'll select a no, element ID of 2112, and then I want to say the Y stress, how the Y stress history will be. So I select the Y stress and I click the plot button. So now you get a window in which it shows the actually it shows the extras history, and you can see all the history for uh, the particular element ID that I have selected. Next is our force history. So force history, again you go to ASCII, and here you can see this SEC force, section force. Again you select the section force, you load the section force, and then you can see I have provided two sections, one at the mid height of the column and one at the top of the column. So if I select uh, at the top of the column, I've selected at the top of the column, and then I click, okay, here plot option will be there. So I click the plot option, I get the section force for the top section. You can see a peak value of 1 meganewton is obtained at here. So this is the response history obtained. So till now we have obtained the response history considering the blast load is applied as a triangular pulse load. So I've already told you we can apply the blast load in two methods. One is applying it as a nodal load considering idealized blast load, idealized triangular pulse load, sorry. And second one is directly applying the blast load. So in that case, so next we'll just look at how to directly apply the blast load. So you have already learned that blast pressure is in the form of a Friedlander wave curve. And here in this section, we'll be applying it as a Friedlander wave curve itself. And here, this is the idealized triangular pulse that we have already applied and we have discussed the results. So to apply the Friedlander wave curve in LS-DYNA, there is an option called a load blast enhance that I'll discuss in detail. I'll explain you how to provide the values and everything. So this load blast enhanced method, it calculates the blast pressure using the Kingray-Burmaz chart, like KB chart that you must have already used the chart to obtain the pressure, impulse and everything. So based on that chart, the keyword, it calculate the blast pressure history. So based on the scale distance of detonation. And then, okay, this is how, like it just explains how the blast enhanced load apply the pressure load. So here in the initial section, we applied it as a nodal load. The triangular pulse load, we applied as a nodal load. So here, how the load blast enhance will be applying is like based on the angle of incidence, the range R value, M value, it will apply the force, it will apply on the segment, and then this will be calculating the nodal forces, and that's how we calculate, that's how the software calculate the blast load. So, so here I have shown you like this blast load will be applied as a pressure. So we need to select the segment or the phase at which the blast load, blast pressure will be applying. So first, that is the first step for applying the blast load using load blast enhanced. So again, we go to create entity section. We click on the set data. So here we have already used set node and set solid to create the response history. So here we'll select the set segment part and set segment, and then we apply the create then we select the create option, and here you can provide a set ID as blast, and then this window will come like we have selected the node set and element set. We'll select the segment set. Segment set is basically the phase of the column to which we'll be applying the blast load. So we'll select the segment set for the blast application. So after selecting, you can see the face of the column will become like it changes to a dark color, and then you can see you can go and click on the apply button. So that's how we create the segment set for applying blast load. And then now we have already selected the segment set for applying the blast load. Now we just have to provide the data for the blast detonation. So you go here again to the keyword manager. You go to the load option, and then you click on the blast enhanced option. So in this blast enhanced option, you have to provide the blast ID. So we'll keep it as 1. We have only one detonation. So here you can see I have inputted M is the charge mass. So here 6 kg charge mass I have used. So it's exactly 6.01. So you provide 6 value also, it's fine. So 6 kg I have provided. And now we have to provide the X value, the coordinate for the blast charge. So we'll detonate exactly at the center of the column. So at the center of the column, mid height of the column, at a distance of 1.81 meter. So here you provide X value is at the origin of like center of the column, X value is 0. So we keep it as 0. But Y value will be our scaled standoff distance. So the standoff distance is from the face of the column to the charge mass. But our origin is at the center of the column. So we need total Y value. We have to keep it as 0.15 as the column thickness, and then 1.81 meter from the face of the column to the charge mass. So together it will consist of, it will be 1.96 meter, and and we'll be providing from the back side of the column. So you have to provide minus 1.96. The Y value will be minus 1.96, and Z is exactly at the mid height of the column. So we'll provide Z as 1.5. And this remaining you can keep it as default value. You click on accept, you click done. And now we have the blast, we have provided the details of our blast, charge mass and standoff distance. We already have the segment to where we have to apply. So now we have to connect these two. So that's how, that's what we do in this keyword. So blast segment set, we click on this blast segment set. So if you go here, you can see the blast ID. Blast ID is the blast ID for this blast enhanced that we have created, and SSID is the segment set ID that we have created, the entity segment set. So you select the segment set ID from here, and then you click on accept button, and then you click done. So now this is the only difference when you are applying the blast load as a as a direct blast load instead of a triangular pulse load. So you can do the previous example that I have done using triangular pulse load. So instead of the triangular pulse load, you delete the triangular pulse load, and then you apply the blast load using blast enhanced option. And remaining all parameter will be exactly the same, only the load application portion will be different. So you delete the node set option, and here you can see like this is including the node set. So you delete this node set option, you just provide this blast enhanced option, and then when you do the analysis using LS-DYNA, remaining all are the same steps, you get the response history. So here I just provided you the nodal displacement history obtained using blast load so that we can compare with the blast load obtained using blast load and the response history that we obtained using triangular pulse load. So we have seen in the triangular pulse load also, we have seen a nodal displacement history peak value of around 1.5. So here also we are getting almost the same pulse history. There will be a slight difference between triangular and blast enhanced, but still this is a comparable result. And here for comparison, I just provided you the sectional force also that I obtained using um, blast enhanced loading. So when you compare with the triangular pulse load, you can see that both section force and nodal displacement are almost comparable. So that's how you do the blast analysis.